We now want to define the magnetic field associated with magnetic sources. But before we do that, let me just remind you how we did this in electrostatics. Suppose we have a source, Q source. And at a field point P here, we put a test charge. Now this test charge, let's make both of these positive. This test charge will accelerate along the line connecting the charges. So this is experimental. And so what we can say is that means that there's a force on this test charge, and that we define the electric field, let's call this the point P, based on the experimental measurement of the force. We say it's the force on the test charge divided by the test charge. And so in this particular example, when these charges are both positive, the electric field will point away from the source. Now, let's just make that a little clearer, that the electric field in this case points away from the source. Now, things aren't as simple in magnetism. And throughout our discussion of magnetism, you'll see mathematically that we'll be introducing a quantity called the cross product. So what we have now is a magnetic source. Let's just draw something like this, a north-south magnet, and we'll take a point P here. Now, we do the same thing. We begin by putting a test charge here, and we ask ourselves if the test charge is at rest, that it feels no magnetic force. So our first observation is that the force magnetic is 0 if Q test is at rest. Now, again, we have to make sure that this is our magnetic source, that the only thing we have to be careful here is there's no electric fields anywhere, so we're assuming now that E is 0 when we do this. Now, the second thing, and this is experimental, is that if we have our test charge that's moving with the velocity v, then in that case, we'll experience, and let's make our test charge also positive, that experimentally this test charge will feel a force, and that force will be, in this particular case, it will be perpendicular to the plane of this figure. So what we're going to see here experimentally is that there will be an experimental magnetic force coming out of the plane of the figure. What that means is the test charge will accelerate out of the plane of the figure. So what we see in the second case, if V is not 0 for the test charge, then the magnetic force is perpendicular to the velocity. Now, over here, we just define the electric field to be the force divided by the test charge. And because the force is not in because the force here was radial between these charges, we could do that. But notice that the magnetic force is perpendicular to the test charge. And so our empirical relation, this is experimental, is the statement that our force on a charge is Q. And this is, in sense, how we're defining our magnetic field. This will lead to define both the magnitude of B and the direction of B. And this particular force law is called the Lorentz force law. So you see, you just can't say that B is force divided by Q because of this cross product. And that's what makes this a little bit trickier than the simple definition of the electric field, which itself was not so simple. Now, for those of you who are not so familiar with the cross product, you might want to review our video on how you calculate cross products and all the properties of cross products, because that will help you understand how we're going to define the magnetic field, its magnitude and direction next.